In the standard model, there are various structures of the particle, like as a gauge structure, Higgs structure, Quark structures, and the Lepton structure. And today I will discuss about the Lepton structures, especially the PSM extensions in the Lepton structures with the various topics. The first topic is the Lepto-Quark, which is denoted by the LQ. The Lepto-Quark is the colored boson, which couple to the quark and the lepton simultaneously. This makes the portal between the quark and the lepton structures. So this Lepto-Quark boson is simultaneously gases covalent under the S3 colors gauge group and S2 left gauge group. So we can denote the gauge charges for this Lepto-Quark LQ, like as 3 or the 3 bar for the S3 color gauges, or singlet, doublet, triplet for the S2L, and some specific hypercharges for the U1. And one can establish the effectively normalizable interactions in the Lagrangian. This Lepto-Quark is the gauge charges under the S3 and S2, so this can couple to the quark and the lepton simultaneously. Here the gamma represented some Laurent structures. Also this is a similar form. Rather than the quark doublet and the lepton doublet, also we can use the quark singlet and the lepton singlet. Then in this case, the pi RQs in the second term cannot have the SU2 charges because this is a singular structures. The motivations of the Lepto-Quarks are the following. In the ground unified theory GUT, the quark and the leptons are embedded into the same multiplet. So such a Lepto-Quark can appear in the GUT theory like as X or Y boson, but not as color built in here. And also in the effective quark-lepton transition coupling can make the portal or messengers between the two structures. So if we integrate out this heavy Lepto-Quark build, because the Lepto-Quarks we expect it is a very heavy mass, so that we can obtain the effective support fermions or operators in the low energy. So like as a quark, leptons are coupled to the Lepto-Quark and the quark lepton, and if we integrate out this Lepto-Quark build, then the remaining operator is just the four fermions operators QQLR. And this Lepto-Quark can have the structures in the quark and the lepton fiber for the Yukawa coupling. Then this can generate the fiber hierarchies and some specific selection rule. Some terms are forbidden and some terms are allowed when we consider the model for the beyond standard model. So we can give such a selection rule by imposing the additional symmetry, like as the discrete J-turn symmetry or other fiber symmetry. Then some dangerous interaction term can be avoided. The dangerous mean that this can induce the fiber changes neutral current process, which is already excluded by the observation. If the Lepto-Quarks exist, it can provide the various interesting phenomenology. For example, in the colloidal search, the Lepto-Quarks can be produced by the hadron collides due to the QCD theory. The possible production channel is the proton-proton collisions, and this can produce the Lepto-Quark, and eventually this decay to the leptons and the quark pair production. And because the quark cannot be existed in the single isolated particle, so the jet will be turns out. So the error, the double lepton, dilepton, and the dijet channel is a signal for the Lepto-Quark. But currently the LHC, the colloid searches, constrains out the Lepto-Quark mass up to the TeV. And also for the proton decay, we should avoid the baryon number violating dichord coupling. For example, in the second term, the Lepto-Quarks also can couple to the two quarks in the Lagrangian level. Then there is the QL from the birth term and the Lepto-Quark and the Q and Q. This makes the dangerous six-dimensional brightness QQQL. This can induce the rapid nuclear decay, especially the proton decay. So one should forbid such a dichord coupling. This can be possible by imposing the additional symmetry like the jet and charges. If we set this such a dichord coupling, QQLQ has a non-zero for the discrete jet and symmetry about the model and congruence. Also, in the reliable physics point of view, such a Lepto-Quark can generate the semi-leptonic brightness. For example, also this is the Lepto-Quarks allowed integrates out in the propagator. So some specific Q is determined by the bottom quark and the strange quark. Then the bottom quarks dedicate to the stranges and the dilepton. So this is a semi-lepton decay of the baryon quark. And for the hadron level, the baryons composes the B meson. So the existence of the Lepto-Quark make the deviations in the B meson decay in the layer channel or semi-leptonic decay channel. But still, the observations are consistent with the other constraint, so that there are no still evidence for the Lepto-Quark. The next topic is the Lepto-Philic and the Lepto-Forbic particle. First of the Lepto-Philic particle, for example, the G prime. This is a gauge boson. The G boson and the lepton coupling is the dominant rather than the G prime and the quark coupling. Convenient parameterization is the following. The first line is just the kinetic term for the G prime and the kinetic mixing term and the mass term. And in the second and the third line represents the coupling between the G prime and the other fermion. Here the second line contains the G prime and the lepton coupling, and third line includes the G prime and the quark coupling. For the Lepto-Philic particle, the coupling GL is larger than the GQ. So what is the benefit of this Lepto-Philic? These G primes usually interact with the dark matters field chi. So that the possible channel is lepton, lepton, G prime, chi chi. So the G prime is the mediators between the dark matters and the lepton. Like that. So by this diagram, we can detect the dark matters. Sorry. Like this form. So this is the standard model particle and the dark matter particle scattering. So and in the Lepto-Philic limit, the Quark and the G boson coupling is very small. So the dark matter and the nucleon scattering amplitude is the quite small, which is the cross sections are proportional to this GQ. So that we can avoid the direct detection between the dark matters and the nucleon scattering because the core coupling is surpassed. But even though that we set this core coupling GQ is 0 at 3 level, but the kinetic mixing between the G primes and the B boson this term generalized the non-zero GQ coupling. But the dark matter nucleon scattering constraints can be avoided, but in this limit we can have the dangerous constraints from the Lepton sectors. For example, the G-2. This G boson contributes the anomalous magnetic moment of the lepton, and also the LEP constraint, electron and the positron collider, and also the neutrino measurement, like the neutrino can scatter through with the electron, and the neutrino trident productions with the G primes is the possible. So the Lepto-Philic G prime can make the extra contributions for this channel. The motivations of such a G prime comes from the anomaly free condition for the gauge theory of the standard model. We can extend the additional U1 symmetries with the Lepton families number, like as L mu minus L tau. This is anomaly free if we assign the charges appropriately. So that we can assume that the G prime couple to the seconds mu and the third tau, these two generations, like the mu, tau, mu neutrino and tau neutrino. But this makes difficult and very dangerous constraint for the LPG minus dual neutrino physics. Now I turn to the opposite situation, the Lepto-Philic. All the same, but the different one is that now the coupling is dominant. Then we can avoid such LP constraint, but such a dominant coupling makes the dijet G primes decay to the 2jet and some resonance in the TT bar signal. And also direct detection limits becomes very strong in the Lepto-Philic gauge boson. So far we talk about the Lepto-Quark, which is a mediation between the lepton and the quark sectors, and the Lepto-Philic and Lepto-Philic particle, also the mediation. But now we turn to the fermion sectors rather than the mediators. In the standard model, the fermion is chiral. Chiral means that the left hand is and the right hand is path that transforms the differently surrounded standard model gauge group. So if we give the representations of the left-handed spinors and right-hand spinor, this is the representation for the left-hand and the right-hand is different. So the if we write the mass term like the psi r bar and the psi r, this is not gauge invariant. So to satisfy the Chiral symmetry of the standard model, the bare mass term is a forbidden, so we should generate the mass of the fermions by the Higgs vacuum expectation value, like as Higgs, L, and R. So if we give some gauge charges for the Higgs, then this term is invariant, and the gauge theory is partially the chirality. But in contrast, in the extended model in the BSM, usually the vector-like fermions are assumed. In the vector-like fermions, the left-hand and the right-hand components in the conjugates each other. So now the representations of the left and the right-hand spinors are the same, so that we can write the Dirac mass exactly without any gauge violation. And the mass terms technically the natural parameters, the bare mass term, so that this can be independent of the electroweak scale. The difference between the Chiral and the vector-like fermion is anomaly structures. If we add the new fermion, then it makes the gauge anomaly. So we should consider the gauge anomalies cancellation condition. But the vector-like pairs always has the difference contribution for the anomalies. So automatically the gauge anomalies cancellation conditions satisfy. So if we assume that the new model like the G prime or GT, usually the vector-like fermions are assumed. Also the G-mass binario cylinders for symmetries for the messenger. One can assume that the discrete symmetry just n in the fermion with the integer charges. So some specific field is transforms with such integer charges in the Zn group. And the operators in the Lagrangian can be allowed only if the total charges satisfy the G's modulus and congruence. So this makes the some selection rule for the model building. For example, we can make the stabilities of the dark matter particle. So some specific operators is forbidden, which makes the lighter standard model it's allowed. So this makes the case of the dark matters that does not occur. And also for the Lepto-Philic and the Lepto-Forbic limits, this can be realized by the charge constraints on the coupling between G prime and the specific fermion. And also we can make the proton stability. Already we said that for the Lepto-Quark, we should avoid the diquark term, QQ and the LQ. So the dangerous proton decays can be avoided. But while the semi-leptonic coupling QL and the Lepto-Quark is allowed about the Zn symmetry. Also, we can avoid the dangerous flavor structures efficiency by using the Zn. So today we talk about several on the various topics in the Lepton sectors, but not especially Lepton sector. This is just the connections between the Lepton sectors and the other one. These topics is quite helpful to build a new model, like as the connection between the quark and the lepton by using the Lepto-Quark or the G prime to link the dark matter. And we can also use the vector like fermions for the additional build. And the discrete J symmetry can avoid the dangerous proton decay or the dark matter decay. So today we talk about the extensions in the standard model by considering the Lepton structures.